All right, so this is the week 14/15 slides. You can find them on Blackboard. I posted them earlier today. And it's just going to go over 6.1 through 6.4. We are going to skip a chapter in here. It's on numerical integration techniques. That section in particular goes over things like the trapezoid rule, the Simpson rule, and a couple other numerical techniques for integration. But I thought we should skip that to pursue some of the other material instead. So having said that, let's get into 6.1. Last class, at the end of it, I showed using the product rule how we can rewrite an integral UdV as UV minus the integral of V du, where dV is equal to dV dx dx, and du is equal to du dx dx. And I said we can use this to solve different types of derivatives, or to solve different types of integrations, I mean to say. We could also use it to solve derivatives, but it would just come back to the product rule anyhow. This idea is called integration by parts, where u and v are differentiable functions of x. And as an example of how this stuff applies, thought we could first look at an actual solid example and then come back to the rules, the general guidelines. So we've got the integral x ex dx. We could say that u is equal to x, or we could say, get another colored chalk, or u is equal to e to the x. Well, if we do that, then dv, it's got to be ex dx. And down here, it would have to be x dx. So the question now is, of these two possibilities, which one's going to help us solve this problem? So what we're trying to do is we want to rewrite this integral u dv as, that's supposed to be a v, as uv minus the integral of v du. So folks at home, of these two possibilities, which one do you think we want to use? The first one looks like it would be the best one, right? Because what we get then, once we apply all of this, would be u would stay the same. It would just be x. dv is equal to e to the x dx. So v's got to be e to the x, right? Minus e to the x. Well, then du would just be dx, right? So solving this integral now, we get x e to the x dx is equal to x e to the x minus the integral of e to the x dx is equal to x e to the x minus e to the x. Checking our work really quick. They set up all the different possibilities here. They say if u is x, then dv is e to the x dx. If u is e to the x, then dv is x dx. Well, in this first case, my mistake. Then we can consider the possibility that one is u, and dv is x e to the x. And then we can also consider the possibility that u is x e to the x and dv is just dx. These are all the possibilities for how we can break this up for our u's and dv's. But after considering all of these, what shakes out to be the best for us is going to be the case where u is equal to x and dv is equal to e to the x dx, which is what we're saying here. Putting everything together now, we get x e to the x minus e to the x plus a constant after we do the integration. And I forgot to write my constant. And if we check it, what are we going to find? Well, the product rule applies here, right? So we're going to get e to the x plus x e to the x minus e to the x plus c. So after all, or plus 0 because the derivative of a constant is 0. So after we take care of the cancellation, we're just going to be left with x e to the x, which is what we were integrating. So we did in fact find our solution. Make sense? So the general process is going to be as follows. We're going to set dv to be the most complicated part of the integrand, and then u to be what's ever left over. From there, we're just going to find dv and du and v, right? And we're just going to shake everything out from there. Honestly, I'm not the biggest fan of their guidelines because I don't know that I've ever come across a set of simple rules for integration by parts that I've ever thought was a decent set of rules. I think this is very much something that you have to get a feel for. It's based off of factoring things and breaking them up, right? Knowing which set of factors to consider. So having said that, let's check out the next problem. The next problem is the integral of x squared ln of x. X squared ln of x dx. Got a couple possibilities here. First, you could be x or u could be x squared or u could be x ln of x, or u could be just the ln of x. Generally, we don't want to set it up so that dx is left as our dv. That's something we want to avoid. Because if you notice, that would just ultimately be the same idea. Does that make sense what I mean? We could play with it, but I can't think of an example I've ever seen where we think of dx as our dv. So having said this, though, of these examples, the one we're going to want to go with is going to be u here. My mistake, it's going to be the ln here. Sorry. It's going to be the ln. And the reason why it's going to be, if this is the case, then dv here would have to be x ln x dx. Here, dv would have to be ln x dx. Here, dv would have to be x dx. Here, dv would have to be x squared dx. Okay, now, with this in mind.
That's supposed to be a dv at the bottom.
Oh, yes, sorry. dv is equal to x squared dx. Okay, now this is where I think the trick is to solving these problems. Recognizing what to do once you started identifying these possibilities. Once you have your dv's, try to stick with a dv that lets you get your v pretty easily. That's the first trick I would look for. This, not going to be easy to integrate. Avoid it if you can. This, not going to be easy to integrate. Avoid it if you can. But these two are decent candidates, right? Now, of the two of these, which du is going to be the nicest one to work with, based on what our v is going to be? Well, here we're going to have to apply the product rule. And we're gonna get 1 plus x, 1 plus the ln of x, dx. And down here, we're just gonna get 1 over x dx, right? Well, 1 over x dx is going to cancel nicely with 1/3 x to the third. So this is gonna be the one we wanna go with. Make sense what I mean? Folks at home, does that make sense?
Yes.
So,
Yes.
Yes. Awesome.
Yes.
Okay, so this is the one we're gonna stick with. Now, in a minute, I'm going to break part of this rule that I just said about not picking either one of those two. That's going to be another problem in just a second. So from here, what we're going to do is we're going to say, all right, well, u is ln of x. V is equal to the integral of dv, right? Which in this case is x squared dx. So v is 1/3 x to the third. Minus the integral of v, again, x to the third over 3. Coming back to our u. U here is the ln of x, so du is going to be the derivative of the ln of x times dx, or dx over x. So now we're going to play that in up here. Now I'm going to erase all of this to make room. From this point on, it is just about simplifying and integrating. So this comes out to be 1/3 the ln of x cubed minus 1/3 the integral of x squared dx. If we wanted to, we could go ahead and factor out a 1/3. But for now, I say just leave it there. Doing the integration here, we're going to get 1/3 the ln of x to the third minus 1 over 9 x to the third plus a constant. And comparing solutions, they say the same thing. Let your dv be x squared dx. Let your u be ln of x. Then your v is going to be x to the third over 3. And your du is going to be 1 over x dx. Putting everything together now and simplifying, you go from here to here. Now we're going to integrate. We get to our solution here. Now, it's not always going to be the case that one iteration of integration by parts will be enough. Sometimes you might have to do 2 or 3 iterations of this. It may be that whatever comes out over here, you have to apply integration by parts to. And that's what I was saying a minute ago about, I'm going to break a rule. It's because those first 2 examples, you would have to reapply integration by parts and keep doing that until you got to an integral that you could solve by hand. So, as another example, and another general rule-breaking point that I was making, I don't know why this didn't occur to me. As an example of when we are going to use or set, rather, dv equal to dx, we can consider the ln of x dx. Here, our factors are going to be u is equal to the ln of x. So du is going to be 1 over x dx. We're saying dv is equal to dx. So v must be equal to x. Putting this all together now, the ln of x dx is equal to the ln of x times x minus the integral of v, that was x, du, 1 over x dx, or the ln of x times x minus the integral of dx. This is going to come out to be x ln of x minus x plus a constant. It's not very often that this is going to happen. This usually only happens when you have, now that I see a decent example, the only other examples I can think of all have just one term for an integrand. I mean, one factor within the integrand. I can't think of any other major examples beyond something like this. I guess some trig functions might. Yeah, trig functions. But anyhow, jumping to the next slide, comparing, they said set dv equal to dx, set u equal to the ln of x, set up your integration by parts, simplify as much as you can, and then integrate. And notice what we get is x ln x minus x plus a constant, the exact same thing we have here. Any questions? So here's an example of what I was talking about a second ago, where you're going to have to apply integration by parts twice. We've got x squared e to the x dx. This is a pretty classic example. Looking at this as an example, you're going to have to apply integration by parts twice. And that's because after the first time, you're going to have x squared e to the x minus the integral x e to the x dx. Well, we just saw a minute ago, we had to apply integration by parts to this. In my mistake, it's supposed to be 2x. I forgot the 2 in here. Minus 2. I apologize about that. But like I just said, we've already seen that we have to apply integration by parts here. Let's go ahead and do it again. Now we're going to have x squared e to the x minus 2, my mistake, 2 times x e to the x minus the integral of e to the x dx. Distribute the 2 and the negative through. X squared e to the x minus 2x e to the x plus 2 times e to the x dx. And now, integrating, we should get x squared e to the x minus 2x e to the x plus 2 times e to the x plus a constant. And just as a note here, we could pull out e to the x. And that's what they do after the integration down here. So just as an example of one case where you have to do integration by parts iteratively. This really happens a lot with exponentials and trig functions. A few times you might have to use it with ln's. Generally, the only time I can think of this happening with anything is going to be x raised to some power times either e to the x or maybe the ln of x. And even then, I think in the case of ln of x, it's always going to be just one iteration. Yeah, it should, because that cancels. Yeah. So a new question emerges though. All right, Matt, well, what about the case where this is supposed to be a definite integral? Let's say we have something like the integration from 1 to 4 of our integrand. What do we do over here? Well, remember before when I had said there's a reason I like to use those square brackets and rewrite it accordingly? The reason is because when we start working with integration by parts, it makes more sense to complete that bracket and say, do all this calculation inside of this bracket, understanding that what you're going to do in the end is the calculation from 1 to 4. Make sense what I mean? So really, working an entire problem through with this idea, we've got 1 to e of the ln of x dx. This thing is going to come out to be x ln of x minus the integral of dx. But after we do the integration, we're going to apply the functional value, a result of this calculation at e. Then we're going to subtract from it the result of that calculation at 1. So now, doing that integrand, I'm going to have x ln of x minus x from 1 to e. So we're going to have e, the ln of e is just 1. Minus e minus x at 1 is just 1. ln at 1 is 0 minus 1. So our answer comes out to be 1. These cancel. This is 0. So all we're left with is the negative of negative 1, which is just 1. That looks like it froze. Did it freeze on y'all? It sure did. Is the video frozen for you guys?
Yes, it's frozen, or I can't see anything.
Okay. Let's try this. I don't know what's happening with the technology. I'm sorry about this, everyone.
I can see now.
Okay, let's get it back to the good camera. That's where the problem is. Cool. All right. And we're back. Dope. Sorry about that, everyone.
Okay.
You'd think after a year of this, we'd have all of the bugs worked out. Okay. So what I was saying, working from start to finish on this. That open back up. Is that when we have a definite integral that we have to apply by parts on, the easiest way to keep track of your bounds is going to be using that bracket notation I was talking about at the very beginning of the definite integral chapter. Where I was saying you have all these different types of notation for this, but the one that I particularly liked was using just this right-hand bracket. And the reason was, later, now that we're here, now that we're here at an integration by parts, it helps to use this notation to pull everything off to the side and say, close the bracket, do everything inside, but keep our bounds in mind, right? That way, we come through and we say, all right, we're going to do this integration, but then later, we're going to apply whatever this is at E and subtract from it whatever this is at 1. So we do that integration, You pass E through, and we subtract one pass through it. That's where this came in. And the result in our case was 1. So having said that, just a couple comparisons for integrals, their integrand, and the techniques that we would apply. In the case of the integral x ln of x dx, that's an integration by parts. But notice if we change the power of that x, all of a sudden this thing becomes power rule. Excuse me. Power rule and the u sum, right? Then if we change the ln of x by a power, all of a sudden we end up at u substitution in the log rule. So very similar looking integrals can end up with very wildly different techniques being needed. Unfortunately, that's just the nature of the beast for these problems. So a common question would be, when are we going to use integration by parts? Like what type of problems can we look at and say, I need it for sure here? Two particularly common examples is x to the n e to the ax and x to the n ln of x. In that first case, set your u equal to x to the n, your dv equal to e to the ax dx. The second case, set your u equal to the ln of x, and your dv equal to x to the n dx. Now I want to make a point about this first example here. Anytime you see x raised to the nth power e to the ax, you're going to need to apply by parts the same number of times as x is raised to. So x is to the first power, applied by parts once. To the second power, twice. Third, 3 times, so forth, so on. Having said that, I think that's all I had to say about that. Now, an obvious question from this point on is, okay, when are we going to apply it? What is this used for in real life? Well, one business application would be calculating the present value. So present value is a way of comparing what you have to what its value is compared to when it started. Does that make sense what I mean? So if you're, how do I want to say this? You've got a bank account that you put $30 in. Maybe it's a CD. And it grows over time. But it doesn't grow at the same rate as inflation. The actual income is going to be what your bank account reads at the end of that time frame. The value, however, the present value, is going to be what this says compared to what it's worth in today's dollar. Get what I mean? I'm assuming the silence is a yes.
Yes.
Awesome. All right, so as an example of what this is gonna look like, you win the lottery for an ass ton of money, and I'm not gonna ask you for a penny of it because that would be unethical of me. So we win a lottery for $1,000, I mean, $1 million. It gets paid back to us as an annuity of $50 for 20 years. I mean, $50,000 for 20 years. Okay. So the actual value is going to be the integral from 0 to 20 of $50,000. If this thing doesn't come back to $1 million, I've screwed up somewhere. So we're going to integrate 50K, integrated with respect to t, comes out to 50K t. We're integrating from 0 to 20. Well, 20 times 50, it's going to be 1,000. So we get $1 million here. Right? So far this looks like we're doing something right. But we want to compare this to what the actual value will be, or the present value will be, assuming an inflation rate of 6%. So this devalues, it is being devalued over time by inflation. That's what's happening here. What this is going to look like is R, since it's 6%, it's going to be 0.06%. T1 is going to stay the same. CT is going to stay the same. So the present value is going to be the integral from 0 to 20 of 50,000 times e raised to the negative t times 0. Sorry, that wasn't supposed to be a percent. It's just supposed to be a decimal. But negative t times 0.06 dt. And jumping ahead, what we're going to do, we're going to integrate this out. We're going to find, hey, in this particular case, we conveniently don't have to apply integration by parts. That's convenient for us here. There are other cases calculating this where we will have to. But when we calculate this out, what we find is that the present value at the end of those 20 years, if we were to compare that $1 million that we just won to its value 20 years from now, assuming an inflation rate of 6%, in today's dollars, it would be worth $582,338. So why does your state like lotteries? Because it says you won $1 million, but it pays it out to you really slow. So what you really won is about half that. Make sense? This is a way of them making more money off of it, really. So now, as an example of where this calculation is going to have to apply, or we're going to have to apply rather, integration by parts to do this calculation. We're going to compare the income of a company, given that its income can be modeled by the equation 1,000 times T. So this is income as a function of time over a 5-year period. We're just saying, okay, year by year, what have we made thus far? Or what are we making currently, I should say. And we want to compare this to what it's actually worth by the time those 5 years are over. Make sense what I mean? So I'll show it another way. Taking the integral of your income function will tell you the total amount of income you've made, right? And the company wants to know what the actual value, the present value will be by the end of those 5 years. If we were comparing it to today's dollars, what would we have actually literally made? What is the evaluation of that dollar? And we see that because of inflation, it depreciates in value. And this is just because the dollar over time becomes weaker. Every currency does this, right? As you have more people, you print more money. So every dollar that's in currency right now is going to be less over time because we have to print out more bills. It's just shares of the value. And this is saying, based on that, how much can we expect the actual worth of this money to be? Personally, I find this really hard to understand and to explain just because the language is so horrible. We're talking about actual dollars in the sense of what we have in physical hand. And then we're talking about the value of the dollar, which is this nebulous concept of comparing what we will have to what we currently have. But doing these calculations, applying integration by parts, setting up the problem, we said that CT is 100,000 times T. So our integration is going to be from 0 to 5 of 100,000 times T, e raised to the negative 0.05 T, integrated with respect to T. We're going to pull out that 100,000. We're just going to run through integration by parts now. Do the calculation. And then apply our bounds. Does everybody follow this? I'm assuming that's a yes.
Yes, that's a yes.
Awesome. Okay, so now we're going to go into section 6.2. 6.2 is all about integration tables. I was actually going to bring in a collection of my books. Integration tables, like there are entire books, and I kid you not, I have a stack of books probably about this, like this. That's just integration tables and other mathematical tables. The integration is the biggest part of it. They're not as common anymore, thanks to the internet. So you see them usually now more like the old head's office, and not so much grad students' offices like mine, but they still stick around because they're useful and not everything is easily solved for the computer. But having said that, what a table of integral looks like is something like these slides here. This is slide 24, 25, and 26 on week 14, 15, which you can find on Blackboard under the exam board. And what these tables are for is quite literally just to help us solve problems. There are some integrals that just take forever to solve by hand. And as a result, it's nice to have these tables. The way these tables are written is assuming that you have already, applied U substitution to your integral. So you keep seeing these integrals written in terms of U du. It's because what they've done here is they've said, assuming you've applied U sub, this is what your integrand should look like. If your integrand looks like this, then this is what your result will look like. That's literally what these guys are doing. That's what these tables are about. So, looking at a problem, we have no way of solving this without applying by parts or something else like that. In this class, we solve that with integration by parts. Yeah, I think we can. It's just going to take a while. But what we want to do, we now want to solve this integration. Your first instinct, what do you want to do? Looking at this problem, nothing really jumps out, right? Can't apply U sub. So it's pretty much already in that most simplified form. And that's what U sub does for us. It simplifies our integral into an expression that's easy to read and easy to calculate. Here, it's already done for us, right? We can't make this any simpler for us. Nothing immediately jumps out here. Maybe integration by parts. But if we have a table at hand, we say, all right, table tells us that the integral of AU over the square root of BCU. Oh no, they didn't write AU up here. Okay. A B A plus BU du. They tell us what that integral is equal to. And this integral comes out to be equal to 2 times the quantity 2a minus bu over 3b squared. The integral, the root of a plus bu plus c. Okay. So this is what the table gives us. So now we come over to our problem. We say, all right, well, we're gonna have to rearrange some of this. When we do, what we're going to have is going to be x over the square root of -1 plus x dx. So a is equal to -1. B is equal to 1, and u is just x. So thanks to this table now, we can find our answer by plugging the value of each of these things into here. So the integral of x over square root of x minus 1 dx, this is going to come out to be 2 times 2 -1 minus 1 times x divided by 3 times 1 squared times the square root of -1 plus b was 1 x plus a constant. From here, it's just a matter of simplifying. But we can already get an idea just by looking at this, what the point of these tables are, right? This would be an ugly integral to figure out by hand. But using a table reduces to just saying, what's our constants and what is it used representing here? That's it. So having said that, as another comparison, this is a trig rule. Yeah, this one's definitely trig sub. So in this next example, we've got the integral x times the square root of x to the 4th minus 9 dx. So the question now comes up, can we rewrite any of this using u substitution? The answer here turns out to be yes. Here, we could say, using u sub, where x is equal to, my mistake, u is equal to x squared. Well, starting with just our radical, we're going to have u squared minus 9, x squared, the derivative of it, is going to be 2x So du is going to be 2x dx. We have x dx, but we don't have we don't have our 2. So we're going to have to multiply this by 1/2 du, right? Make sense? So from here, we're going to go ahead and try to rearrange this to get 1/2 the integral of u squared minus 9 to 1/2 power du. So now we come to the table and we say, all right, we've got everything as simple as we're going to get it. There's nothing else we can do here to make this any prettier. So let's go to our table. Come over to our table. Our table tells us that the integral of a squared minus x squared, right? No, it's u squared minus a squared all to the 1/2 du. Our table tells us that this thing is equal to, oh my God, that's ugly, 1/2 u times the square root of u squared minus a squared minus a squared times the ln of the absolute value of u plus the square root of u squared minus a squared plus a constant. That's ugly. Nobody has time to find that by hand. Nobody wants to find that by hand. So now we have to come back and say, all right, what is our u's, what's our x's, what's our a's, blah, 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 right? Well, here, our u's are going to be u's, right? Because that's how we've rewritten this. Our u's in the table are going to correspond to our u's here. Now we've got A is going to be equal to, in this case, looks like 3, right? So a squared is equal to 9. So A is going to be plus or minus 3. And this is just good to note for down the road, in case we were going to do something else with the calculations. Because you notice here, every time we see A, it's always A squared, so we can just leave it as 9. But this is just something good to pay attention to, just in case later. So from here, we're going to say, all right, just plug in 9 to all of these A squares. Then come back to our u sub and apply x squared to all of these u's. And that's all it is. You say, cool, got our table, figured out that 9 is equal to a squared, and u, because of u sub, is equal to x squared. Plug them in. You're good to go. So this is really the whole idea behind using these tables. There's nothing insane, nothing crazy here. Any questions about this? Having said that, there are some points in the table where the solution is written in terms of another integrand. So as an example, what do we do here? How do we handle this? Well, once we've gone through and applied the table the first time, we're going to apply the table again, or do whatever it takes to solve this integral. And we keep doing that until the problem's solved. So as an example, that same exact formula I was just pointing to. Let's say we've got the integrand of the integral of x squared e to the x. We're going to go to our table, apply formula 36. We're going to say, all right, cool. We've got everything set up. Go back to our table because here's another integral. We know how to solve this now, but before we didn't. So we go back to our formula or our table of integrals. We say, all right, cool. We've got another formula we can apply. Apply it and solve. Is everybody cool with this idea? Makes sense? Yeah. Folks at home, what do we feel like? Feel good with this?
Yes.
Yes. Awesome. All right. In that case, I'm going to keep chugging along. I don't have time to get into anything else. What is left is the final section, 6.4. So next Tuesday, we will go over 6.4. And then after that, I'm just going to review for the rest of the day. Get ready for the exam and the final. So come ready with your questions Tuesday and next Thursday. Because 6.4 shouldn't take too terribly long. If you have any questions, I'll stick around, but otherwise you all are free to go.